everybody, and thank you very much for joining us today at Synaptec for this webinar, which is taking on a deep technical dive in aspects of wide area monitoring and control, and in particular mixed circuit protection, which seems to be a very popular application and we're getting a lot of business on. So the objective today is to take you through this, not from a commercial or practical perspective, but by inviting some expert witnesses. So we have Bogdan, our consultant, who is a lead engineer at SEL, and also Steven Blair, who's our power systems lead here at Synaptec, and they'll be guiding you through most of this presentation. A few housekeeping notes. We will always try to keep this whole thing within the scope of the hour that we allocated for the webinar. This is one of a long series of webinars, and after this event, we are recording it and we will post the whole thing up to YouTube so that later on, if you don't remember something or you weren't sure, you'll be able to rewind that, and we'll give the people who registered and attended this event specific access and early access on your own to that content for a while, so that you've got a reminder of what was covered and you can see it all again. That said, on our YouTube channel, you will see previous webinars that cover a lot of this material and other applications that we do. But for today, we're going to take you through these slides, explain some of these concepts and how we deploy our technology. And as a request, we'd like you to use the chat channel, not the Q&A channel. The Q&A is not enabled in this version of Zoom, but chat is. If you want to post questions for any of us in the chat, we'll do our best in the background while Bogdan and Stephen are talking to answer those questions or pick out the most important and frequently asked ones at the end of the session, because very often people ask the same thing but at slightly different times. So if we don't reply to you immediately, don't lose heart. We don't ignore you. We will follow up with everyone who's asked a question and make sure we capture everything. So with that said, and with plenty of you now joining, thank you for giving us your time. Let's dive into the slides, which we hope everyone can see. The agenda today is to remind very quickly everybody who we are and where we fit into the universe, and then I'll try to get out of the way as quickly as possible and leave it to the experts to speak. So very quickly, who we are. If you don't know Synaptec, we just celebrated our 10th anniversary, and apparently it takes 10 years in the power industry to become an overnight success. But we've been beavering away here, developing a technology that we patented 10 years ago, which is distributed electrical sensing. This is the idea of distributed sensors, something that can measure things like voltage and current far away from the substation, but completely passively. They're actually passive sensors that are connected by light and not data through optical fiber networks, which means it's extremely fast, extremely long range. And at the remote location, you don't need all the traditional surrounding infrastructure that's typically required. Things like control power, copper wiring, merging units, access to a telecoms network, or some kind of power scavenging to drive a 5G device for IoT sensors. These are genuinely passive sensors. And because they're passive and because they're small footprint and in fact very fast and easy to implement, new or as a retrofit, it radically reduces the capital cost as well as the carbon footprint of instrumenting a complex power system. And on top of that, as well as the capex savings, it reduces outage time and repair costs. So typically our business falls into two big camps. We're very active in transmission, but also offshore wind. We're specifically focused on complex feeder protection and providing differential protection schemes for complex and challenging circuits like these ones that contain overhead lines and underground cables. But also we have a significant business in condition monitoring, where we are just remote monitoring high value HV assets and looking for early warning signs of problems as well. So if this webinar doesn't quite get to what you're interested in, please talk to us, leave a message in the chat, and we'll endeavor to help you and follow up with specific needs, because everyone's always got a very particular thing that they need to focus on. Very quickly, the industry challenges we address. I don't think this is a surprise to anyone, as the whole world tries to decarbonize and move to decentralized generation and tries to digitalize and leverage new technologies for cost savings and improvement in control. We're just saying this is a good time to bring a product and a technology like this to market, because power networks require more distributed measurements in more awkward, remote or inaccessible locations to have that granular visibility and control of these assets, whether it's about integrating renewables, repurposing that legacy infrastructure to cope with all that change, simply reducing cost while in guaranteeing availability and resiliency. This technology helps. And in our initial deployments in transmission in high voltage networks, we quickly realized that compared to traditional or a standard and conventional ways of instrumenting remote locations, if you remove the planning permission and zoning, if you remove the civil works, if you remove things like the copper wiring and the control power and the active electronics and the data networking that's required, the data networking cost alone would radically reduce in this scenario where Synaptec can offer effectively half the cost of deployment of sensors in critical locations. So as the world decentralizes and digitalizes, this allows people to put more eyeballs in more locations to monitor what's happening with high levels of fidelity and reliability over the years. So distributed electrical sensing is an umbrella term for what we talk about when we discuss these distributed sensors. And the industry likes three-letter acronyms like DTS and DAS. So we followed it and said, well, DES is another one of those. But you'll see it deployed across digital substation trials, mixed circuit protection that we're talking about at the top here today. It also works very well for complex feeder protection, monitoring remote overhead lines for things like ice buildup or damage. It's also being deployed now in urban areas for high voltage and medium voltage cables that are under the city, trying to provide early warning signs of more failure modes in more locations that are critical so that we can completely avoid outages and reduce risk. And that's why we've also got a booming business in offshore wind, where you'll see the world's largest wind farms, such as Dogger Bank, completely reliant on our monitoring the control technology to look at all of those subsea cables and provide early warning of problems so that we can completely avoid outages and save tens of millions of dollars. Now, DES will be explained to you by Steven and Bogdan better, but right now, the message that we wanted to convey was very simple. If you can put a sensor far away from the substation and virtually look over the fence at somewhere remote or inaccessible, you can install it quickly. You can never come back. You never need to come back to check it, to refit it, to repower it or replace batteries. You never need to maintain it or recalibrate it. You've got this ultra stable platform that will operate over decades with no intervention and give you that long range and long distance, but synchronous and permanent visibility of something. It's about seeing everything everywhere all at once and bringing information back to the center, and only inside the substation firewall are we creating data. We're using standard component 6 on the outside to get that information in, and standard algorithms and software on the inside of the substation to provide critical information at unmatchable speeds. And I say unmatchable because by definition, if we're using light, nothing else is faster in the universe to come back to the center and tell you what's going on. So that sounds like a crazy claim, but we'll now pass over to Steven and Bogdan, who are going to explain how this relates to mixed and complex circuit protection in more detail. Steven?
Okay, thanks, Al. So I'll get started about sort of describing what the problem is here and with these mixed circuits, and talk about the solution that we have available for that. And then Bogdan will follow up after that, going into some of the more interesting kind of general applications that this enables. So what do we talk about when we say mixed circuit or a hybrid circuit? It's simply a circuit or a feeder that has a combination of overhead lines and cable conductors in series. And there could be more complexity to that as well. Like there could be multiple parallel circuits in one particular transmission system. So why does this occur? Well, we're seeing this is occurring quite commonly. And usually it's because of, some fairly obvious kind of geographical sort of limitations. Like there could be a river or lake in the path of the transmission circuit. So that might require undergrounding. Another example, which is what this photo is from this slide, this is a substation beside the airport in Madrid in Spain. And here they had to underground a 12-kilometer section of circuit because there was going to be a runway there. So there's lots of different reasons. There can also be just, for aesthetic reasons, that it could be desired to underground part of a circuit. Also, another factor is there could be a relatively short span between the substation and the first overhead line tower, and there might need to be there might be some clearance issues there that require it to be undergrounded. And then also sort of in the background, there are some general reasons about why we're seeing undergrounding of circuits. variety of reasons. That could be simply for better reliability, or it could be for better safety. If you think particularly maybe if there's like a farm or a village nearby the overhead line, that could be preferred, or simply like a government policy where there's like in Denmark, where it's just a strong preference for undergrounding circuits in general. So what is the problem that creates for protection engineers? It's due to the fact that there's different circuit types or different conductor types along the length of the circuit. And commonly, the protection system will try to reclose for faults on overhead lines. That's generally the good strategy to do to, improve the security of supply and get the power back on right away. But for cable sections, it's important to block reclose because generally those are permanent faults if they occur. And reclosing on them perhaps can just make things worse, can create a safety issue or cause even more damage. So the important capability here is this kind of protection word discrimination, which in this case is a good thing. So being able to discriminate between faults in overhead lines and cables sections is very important to enable an appropriate auto reclose strategy. So that's essentially the problem we're trying to solve here. And that can be quite difficult using conventional technologies because they can be impractical or they don't give you perfect discrimination of that location of the fault or which circuit section it appears on. So that's essentially what we're going to kind of talk about now is Synaptec's approach to that. There's a really interesting and useful Sigure report, which happens to be being published exactly 10 years ago, right when Synaptec was first created. And this report actually did find Synaptec's technology, which was very new at the time, and it did describe it as essentially the perfect solution to this problem of discriminating between the auto reclose on overhead lines and cables. The only issue at the point is Synaptec had only just started at that point, and we hadn't made a kind of industrial ready product at that point. But we've obviously resolved that in the meantime. So what does the solution look like? So basically, if you're trying to make a decision here about to do this discrimination using just information that's in the substation, it's really hard to do that correctly in real time. Distance protection is very difficult, for example, because you've got different impedance profiles of the different conductor types, and in particular, cables might have a non-linear impedance profile as well, so it's generally not effective. And installing sensing using conventional approaches at the transition points where you'd need to have CTs installed can be very expensive fundamentally because you need a lot of infrastructure there, and that can cost a lot of money. It might involve building an entire substation to make that happen. And even if there's an existing substation, there might not necessarily be enough space to put all the equipment in these remote locations. So that's essentially what we're solving here with the passive sensing, as Sol introduced earlier. So what we allow to happen is to put CTs in these exact locations where they're needed around the insulated cables. This can be retrofitted quite readily. And the CTs go through our passive secondary converter, which doesn't need any control power or data telecoms. It just needs a connection to the CT secondaries and to the fiber. So this is something that's quite simple and relatively inexpensive compared to any other potential solution. So just to flesh that out a little bit, this diagram kind of shows you what that looks like. So we have a device in the substation, which looks like any other kind of substation IED, which we call the interrogator, and it basically illuminates the fiber. And then at each sensor location sends a reflection back completely passively. And each sensor is kind of effectively coded to a specific wavelength of light. So the interrogator is able to look at these reflections and from all of the sensors simultaneously and recreate the waveform data from all of those CTs back in the substation. So it's kind of giving you a central view of lots of sensors that can be physically distributed over many kilometers. And the interrogator outputs kind of standard waveform samples, and we can produce 61850 sample value data streams, for example. And then that enables a lot of applications potentially building on that. So I'll focus just on this problem of how we solve this auto reclose problem, and then Bogdan will expand on that with some more kind of general feeder protection applications here. And just to kind of show a little bit more physically of what that would look like, you would have maybe an interrogator and some local passive sensors in the substation, so they could connect to existing CTs if they're already available. And then we'd install CTs on the insulated cable on any cable sections at remote locations. And then, as I say, all they need to get the measurements back to the substation is just a connection to a fiber, which is, usually it's readily available in these, particularly in these transmission networks. So here's a couple of examples of what this auto reclose solution looks like. So the diagram in the top right shows that it could be a very short section of cable that goes from the substation to the first overhead line tower. But conventionally, these are a challenge, and it's just inconvenient to be able to deploy differential protection on those small cable sections. So I think it may depend on the operator's protection policy, but I think conventionally those cables are kind of ignored, and if there is any fault on that feeder, the system will auto reclose, which is obviously not desirable. So this solution kind of completely removes that pain point and removes any risk of damage or safety effects if there was a fault on that cable section. And then the lower diagram here shows a very similar solution, but the cable section to be monitored is a remote, potentially tens of kilometers away from the substation, and we're able to put passive sensors on each end of that cable. So what this does, as I kind of already alluded to, is we can make a differential protection zone around that cable section and multiple cable sections if they exist on that circuit. Using the real-time measurements that are available from the interrogator, we can make a very fast protection decision. So there's nothing really groundbreaking in the protection algorithm itself. It's differential protection that is well known and is well understood, but we're able to just leverage that by using these new measurements that we make available conveniently to give it a cable protection solution. So what that means is we can essentially provide a simple signal to the main protection to advise whether to block reclose or to allow it, depending on where the fault has occurred. So here's kind of physically what it looks like for one of our installations. This is in India, where you can kind of see this is our older style of CT and passive sensor. We have a kind of more robust approach now. You can see that CT is installed around the insulated cable as it's going up to the bushing at the transition point. And then we have the interrogator in the substation kind of panel here, and also we have our kind of local passive sensors in the substation as well. And then that all combines to produce the mixed circuit protection solution, which provides a signal to the protection to advise whether to block or allow auto reclose. This slide is kind of showing you the extremes of operation that we can provide. So this was actually something we presented last week at the PacWorld conference. We have a customer which had quite a challenging requirement for us, which is to deploy a cable section that's quite far away from the nearest substation. And in the worst case, it required us putting sensors that are about 62 kilometers from the substation. So it's kind of out in the middle of nowhere, and we were able to kind of engineer a solution that worked effectively. And despite those distances, we can still perform the protection as normal, and it still provides sub-cycle trips for cable faults, and then for which it provides a blocking signal to the protection. And then for an external fault, which in this case is an overhead line fault, we do not issue a trip. So it means we allow auto reclose to operate as normal. So this is kind of an edge case, but I thought it was quite interesting that shows the kind of scalability of this sort of solution. We can solve this problem even for kind of the most challenging examples that are right there at very long distances, and we can kind of completely resolve this challenge of the sort of conditional auto reclose. So this is kind of a bit of a taster of what's coming up in a moment that Bogdan will elaborate on, but this concept of having multiple zones of differential protection that are outside the substation, we can expand that to basically any sort of topology of circuit, and we can provide, in the more general case, we can provide differential protection of those feeders, and that could provide a lot of additional benefits in terms of fast acting, very reliable and dependable protection on these feeders, particularly at maybe like sub-transmission levels where having that extra visibility could be really valuable, particularly if there's, new generation connecting in and the circuits are getting more complicated as a result. So basically we can do a kind of more generally, we can do multi-zone differential protection of kind of complicated circuits. And you get the data from all of those sensors, all of the CTs are available centrally. So one example of that, which we've deployed here in Scotland, is with SSE Networks, and we basically were able to instrument a three-ended circuit, but all of this was done passively, and it didn't require installing any kind of active electronics at the remote locations. So we're picking up all of the CT measurements passively and getting them back to a central location. So that allows for significant cost savings for, again, this typical case where a new generator needs to connect in, and so providing the kind of main protection, the differential protection for that is a real headache, and relying on distance protection is possible, but it's becoming increasingly difficult to validate that and to design it in the first place. So this provides a kind of neat solution that's well understood. It operates, it's highly dependable and provides that perfect discrimination that you'd usually expect from differential protection. And again, here's just some more photos of this. Again, this is an older style of kind of outdoor unit that we have. We have a kind of more ruggedized form factor nowadays, but that just shows our system installed out in the kind of the substation yard, and then also our protection device and interrogator inside the substation. So I'm going to stop there. I'm going to hand over to Bogdan, who's going to kind of elaborate on that. So thanks.
Thank you, Steven. Let's talk more specifically about protection. So the roots of the technology and the first applications were really about controlling auto reclose, and that's relatively safe operation. And from this, we are going to graduate now to protection. Steve, if you could grant me the, thank you. So first, let's summarize briefly what mixed power lines are. So mixed means they're still two-terminal, but they have multiple sections. Before the Synaptec system, we had to abandon auto reclosing. Now we could do auto reclosing. Distance protection faces limitations because of impedance non-homogeneity and variability in the zero sequence impedance. In theory, it's a two-terminal circuit, so we could use a line current differential or directional comparison schemes to protect it end-to-end. That requires a channel, of course. The fault locator faces challenges, and then if you have cables, you may think of the incipient cable faults or the packing faults that last for a very short time. And traditional protection will have difficulties detecting those faults. And in the new solution, we will see that we could do something about those faults. When you compare it with a complex power line is, say, a distribution feeder. It is a multi-terminal line, meaning it has multiple branches and spurs. So by necessity, it's a multi-section line. At the distribution level, so medium voltage networks, we keep using the time over current protection, And that's a very poor way to protect that circuit. It has low sensitivity, slow operation because the coordination intervals stack up. Down conductor and high impedance fault detections are very problematic despite the dedicated products that are meant to do it. And recently, there is more and more talk about wildfire concerns, and that has to do with insensitivity of and slow operation of time over current protection. At subtransmission levels, you could switch to unit protection, but that requires a line at each terminal and a channel to each of those relays. So that becomes really expensive and kind of convoluted. Distance relays are better than overcurrent relays, but they are not a game changer. Faulted section identification is difficult, and traditional fault locators, the ones that use measurements from the substation, they don't work, right? So what do we do about it? Well, once we are able to scatter CTs, or in general PTs too, but all we need is CTs. Once we are able to scatter them throughout the feeder, we put differential zones. And it's my choice how many CTs and where they are. And once I have a differential zone of protection, the life becomes much easier. There is nothing better in the protection world than differential protection. Of course, detecting a fault is one thing, clearing is another thing. I could only trip the breakers and reclosers that I have, but I could make my fault detection as granular and as sensitive as I have to or want to. So multi-zone differential protection is a common solution for protecting both mixed and complex circuits. It works by dividing the circuit into small protection zones, ideally 2 terminal or 2 current zones. That gives me transmission grade performance in terms of speed, sensitivity, and selectivity. Allows best possible sensitivity and speed for those difficult cases when I have a high impedance fault, such as a tree contact or a down conductor. Mid-span or clapping conductor faults are really difficult when you have a wind and the conductors slap. The fault lasts for a brief moment. A time over current protection is not going to time out. Yet you have arcing, you have high energy, and you could start a wildfire. Incipient cable faults, wildfire reduction, public safety improvements. So there is nothing better than differential protection, right? That solution allows multi-ended impedance fault location. And I will have a slide on this. And in short, that future-proofs the application towards things like distributed energy resources, and also allows wider use of those complex circuits with a driver to just save on primary equipment, right? So once we are able to protect and operate those circuits better, then we could have those circuits and save money on the primary equipment. So if this is so good, why don't we use it today, right? It's a good question. So, conventionally, if you wanted to provide measurements from outside of the substation fence, you will have to put something together that I'm showing in those pictures. I call it a micro substation on a pole. So think about it. In order to provide measurements, I will need some form of a relay or an IED. I will need a high bandwidth, low latency, and dependable communications channel from each of those measurement sites. In order to have an IED in the first place, I will need to provide control power. How do I provide the control power? Well, I could drop a PT, potential transformer, to run my IED from, but then for a backup, I will need a battery and a charger. This is electronic, so I have to put it in some kind of a cabinet to protect it from the elements. I need to provide a crew access for maintenance and testing. And that orange ladder in the picture here, I don't think anybody wants this as a crew access to work on that site. Physical and cyber security are a concern. So This is theoretically possible, and we do it today for reclosers. But as the pictures show, this is quite convoluted and quite ugly. So the Synaptec's distributed electrical sensing system solves those problems at the expense, or the two enablers are having the technology and having the fiber, and that could be all dielectric self-supporting fiber that is way cheaper or economical than the ground wire fiber. So when I have that, I could put my desired zones of protection around branches or sections of that feeder. I could do it with different granularity. So I could have all sections kind of instrumented individually for better sensitivity, or I could have longer runs depending on my applications. Maybe only a section of that feeder is problematic, such as subject to wildfires. So I could spend my differential zone only there and leave the rest of the feeder protected using traditional methods. But in any case, small differential zones are better for sensitivity, speed, selectivity of auto reclosing. Differential will work with default settings. There is no need to really do complex setting calculations. I will have optimum backup. So for example, if I am to provide backup for faults in dead load here, I will use this remote CT with a time over current function coordinated with the load. And that gives me a way better solution than today using the CT at the substation that measures the total load current of that feeder, right? I could provide backup for loads and DERs. Impedance-based fault locating is possible. Because differential protection is not impacted by the inverted base resources constituting those DERs, I just build my microgrid enabler, and through the sensitivity and speed, I dramatically reduce the danger of power line caused wildfires. So the integrator, so the box that digitizes the light and provides the measurements, already includes differential protection elements. Today you have up to 10 zones. The operating time is half a cycle. That's an extremely fast protection. Dual slope phase segregated. You could have up to 3 currents in any given zone. All of that is just firmware that could be improved and changed and expanded. Contacts or goose to actually trip the breakers. There is a time over current built in today for backup, and the box is built to withstand harsh environments and complies with the 60255 EMC requirements. So there is no need to even go with sampled values to standalone relays to provide differential protection, or also you can do that. Differential protection is already built into the integrator. Let's talk about protection security. So we are talking about tripping using the provided technology with relatively short field experience compared with your traditional relay manufacturers that exist for 100 years. So how do you ensure security? Well, one thing you could do is in your existing relay, you could put the overreaching zone 2 for phase faults and the ground directional protection for ground faults. So these two elements will detect the fault anywhere along that mixed circuit line and also faults outside. And then I will build or apply 5 zones of differential protection in order to protect each section individually. I may also put a check zone that balances the currents at the terminals of that circuit. So now in terms of the secure tripping logic, if I have a fault in zone 2 and 4, that's a cable fault, so I may block auto reclose. If I have a fault in zones 1, 3, and 5, that's the overhead line fault, I will allow auto reclose. The or of the two is a fault anywhere along the line, so a request to trip from a differential. And then to secure this, I could supervise it with the detection of a fault through a distance and ground over current directional in a separate relay. And also I could supervise it with a checksum. So that trip command now, it's extremely secure. I really don't have to worry about tripping or a false trip. And at least for the first year or two of the application, or for the first few applications, that's what you could do to absolutely ensure that there will be no false trips, even though the technology is relatively new. Fault locating. Because I have measurements throughout the feeder, if I detect the fault in the section 4, what I could do is I could invoke a double-ended fault locator to get me the fault location, and I will feed that subroutine with the impedance of that section. So that's my setting Z4. And then I will feed it with the measurements voltage and current from one terminal and voltage and current from the other terminal. I measure the currents directly, and for voltages, I will calculate them. So it's quite easy to pick up the voltage measurement from the substation. And then knowing that this section is fault-free, I just take this voltage and compensate it for the voltage drop across that section. And I just received or calculated the voltage here. I continue compensating, so I got this voltage, and finally I get V4. I use the average of the two currents before multiplying it by the impedance. Of course, this is done on a 3x3 matrices to recognize the three-phase power system. But I use the average in order to improve accuracy for cases when there is maybe a small unmeasured load hanging here at the top, or there is a charging current that I want to reduce that. I do the same to calculate the voltage at terminal 5. And from that point, I have voltage and current at both ends. I call the double-ended fault locator subroutine, and I get a fault location with very good accuracy, even though I only measure currents throughout the feeder, and I use voltages only from the main substations of that mixed circuit. So quite elegant, quite simple to do. This is not available today, but again, this is just code that could be added, will be added, and that's a great leverage of the existing measurements. Last topic is the packing faults. So the incipient cable faults, they start as a part of discharge. They are self-clearing at the fault at the current zero crossing. Joints are susceptible because even though people use machines, it's still done kind of by hand in an uncontrolled environment. Some data indicate that about 15% of faults are incipient before they turn permanent. The permanent failure could happen in few cycles to weeks. You could have one or hundreds of incipient faults before a permanent failure. And of course, because the fault lasts so short, traditional protection will have issues detecting it. Now, with the Synaptec system, because it's differential and it's fast, you could detect those faults, and you could do something that is more sophisticated. You could have a counter, and that counter could count the number of incipient faults within a given cable section, and alarm based on the certain count, and trip based on another count. Also, you could run an algorithm to detect the repetition rate, and if those faults tend to appear more and more frequently, you could trip based on the repeat rate, because if they appear more and more frequently, chances are that the permanent failure is approaching. So today, this can be done in the SCADA HMI environment when the pickup of the differential function is provided, say, through the goose messaging. Something like that will be added in the interrogator based on the business case, and we will have an ability to really detect those packing faults quite reliably and kind of complete the story of cable protection. So with this, I will pass it back to Steven for a summary.
Great. Okay, thanks, Bogdan. Sorry, slight delay in getting control of the mouse back there. Okay, yeah, so this just really to sort of consolidate what we're saying there is that this is a kind of relatively new way of providing protection over large areas of the network that previously were really inaccessible to install measurements. And with that, it opens up a lot of new possibilities for protection and control. So just to reiterate, what I focused on was our approach to solving this problem of discriminating between cable faults and overhead lines, overhead line faults on mixed circuits. So we provide quite an elegant way of completely resolving that problem by basically being able to deploy differential protection, and including even for very challenging circuits which are very far away from the nearest substation. And then obviously we just heard from Bogdan, who gave quite an interesting description of where this can go in the kind of long term and how this can scale up to provide a quite interesting solution to solving a kind of multitude of different problems that are emerging on kind of distribution and maybe sub-transmission networks. So hopefully that gave you a kind of taster of the technology. I think we'll now move into the Q&A. So maybe Saul, would you like to?
Yeah, I can do that. Thank you, Stephen. So there are actually a couple of questions that were going on in the background here, and maybe I can throw Stephen or Bogdan under a bus to answer them as we go through it. The first one, Stephen, actually, I've seen this a couple of times, but it obviously bears explanation because the question does come up. So the question was framed as, what is the current capacity of our CTs and the accuracy? So I think it might be helpful to explain again the distinction between the industry standard CTs and how we secondary connect, and therefore, you know, dynamic ranges and accuracies and how that all interplays. Could you take that on?
Sure. So there's a bit of a sort of trade-off really on the selection, but usually we'd be targeting sort of 5P20 CT, that kind of accuracy class. And we're flexible in what's needed for particular applications, but that's typically what we would want to deploy. So yeah, essentially that gives you 1% accuracy at nominal and 5% accuracy at fault current levels, and that typically is what our customers are looking for. So was there another part of that question, Saul?
Not really. I just thought it would be helpful to explain that, like, we're not inventing some newfangled kind of primary transformer. We're not doing a Faraday effect. You know, we're trying to use standard iron core CT. So in that sense, dynamic range is given to us, right, by the customer. They'll say 5P10, 5P40, whatever, right? It just depends on the CTs.
Yeah, absolutely. Yeah. So well, there's not really anything necessarily new here in terms of what customers are used to dealing with. It's standard off-the-shelf CTs, and we just connect to the secondary in the same way that any protection relay would connect to the secondary of the CT.
I think in general, people were have also asked, like, to distinguish against the Faraday effect type of optical CT. You know, we're talking about something that sounds optical, but it's a different kind of optical. So could you just distinguish that so it's clear when we're not talking about this light polarization by winding the fiber around the conductor? I think that's important because it speaks so much to the robustness and resiliency of what we do.
Yeah, exactly. So I think the key differentiator here is like scalability of the Synaptec approach. It's more efficient in terms of the use of fibers. So we can install, say, 25 to 30 sensors per fiber, whereas the Faraday effect technology requires much more fibers to be used. So it's a bit more convoluted to do it that way. Also, the distances that they can achieve is maybe sort of quoted usually in the range of sort of 20 to maybe 30 kilometers doing it passively. Whereas as I kind of expressed earlier, we can do that, at least double that range. Another factor that I think is also quite interesting, I think, is that, I mean, you mentioned already, Saul, that the Faraday effect, it requires, sometimes wrapping the fiber around the conductor. So that's work that has to be done on site to retrofit to an existing cable. Whereas our solution would be, it's just a standard split core CT that can be quite easily fitted around the cable and doesn't require kind of complicated and sort of fragile wrapping of fiber on site.
Got it. Thank you. Maybe just to share the burden here then, or the load. Too many industry puns. I'm sorry. Let's flip over to Bogdan. Bogdan, one of the questions was about, you're talking about multi-zone differential protection. So what that zone is made of, I suppose, doesn't matter. So, we happen to be talking about cables, but it could be a transformer, right? That the principle would be the same.
Yes. So, I mean, it's not often when you have an inline transformer, but it may happen. So differential is differential. Today, it's not available inside the interrogator, but you could put the sampled values from the interrogator into a transformer relay and span a transformer differential zone across the transformer and the buses and the feeders that are coming to the winding. So with this, sky's the limit. Once you gain easy, reliable access to measurements from outside of the substation fence, things become really easy. Or you have access to extremely powerful technologies. Obviously, what is the zone? In protection, the zone can be defined by the boundary of measurements. So the CTs, this is where you will see the faults as internal. But when you have a fault, you have to clear it. So another definition of a protection zone is a boundary of the current interrupting devices that allow you to cut that faulted part away from the rest of the healthy power system, right? So, in this application, you are allowed to make a distinction between the two. So you could have small differential zones to detect the faults. So that gives you sensitivity. But then when you have to clear that fault, you trip the breakers that you have and the reclosers that you have, right? You cannot trip breakers that you don't have. So quite typically, what will happen is that your clearing zone is going to be much larger or larger than your fault detection zones, but that's perfectly fine because you are going after sensitivity, after speed, with time, as you keep adding reclosers to that feeder, maybe your selectivity in terms of isolation and feeder reconfiguration will improve. But in terms of granularity of detecting the fault and sensitivity, you could go all the way to having each branch of that complex feeder covered with one 2-terminal differential zone. So that's extremely powerful. Once you deploy that system and you get the measurements, some people hate the term future-proof, but that is future-proof. You could keep adding DERs, you could keep complicating that circuit, and you are still fine because you are using the most powerful principle there is for protection.
Very good, thank you. Right, a couple of other questions that have come in. There's a deep one here that I'm definitely going to defer to Steven or Bogdan on. So if connecting existing CTs in the substation that are already in service, is there an impact on the performance of those CTs? So in terms of accuracy, class, or burden?
I think the answer is yes, but I think Bogdan can probably correct me here, but I think the CT will have like a rated burden, and I guess the total kind of load on that CT, it would need to be calculated, and if it was within the rating, it would be acceptable. Otherwise, you'd need more CTs, I think. Does that make sense, Bogdan?
Yeah, I mean, the burden resistor is, what is it? 1 ohm?
Typically 1 ohm is what we
1 ohm. So you are burning that CT a little bit more than connecting a modern digital relay, right? A modern digital relay would have a small fraction of an ohm, but you still have the CT secondary resistance, the winding resistance. So the impact is basically connecting a 1 ohm burden, which is not devastating, but in theory it has an impact. So that's really the only kind of consideration, that you are adding a load to that CT that is 1 ohm, resistive 1 ohm.
Ready, thank you. Right, I don't know who's best placed to answer this one. It is, do you see an issue with screen bonding strategies for cable fault detection?
Yeah, so I think what this question is getting at, and I didn't really go into the details of this, but when we install the CT around the insulated cable for these cable sections, then the screen or the sheath should be fed back through the CT, so that it's getting fed back in the opposite direction from what it's inside the insulated cable. So that basically cancels it out. So what that means is the CT is only measuring the phase current in the conductor, so because the screen's cancelled out. There's also a useful side effect of that. It means if there's a fault on the bushing at the transition point, then the system will actually block auto reclose for that as well, even though it feels wrong because it's outside of the protection zone, but because of the way when you kind of simulate the fault current flows, that it will trip because the screen is fed back through the CT. So, but that works out as a kind of a sort of a bonus capability that is useful, I think, because it would be undesirable to reclose for those faults as well. So it's not necessarily an issue, but it does need consideration in the kind of for the design, for the installation of the system, that there basically needs to be enough space. The diameter of the CT needs to be big enough to go around the conductor, which might be huge on its own, but also to allow space and consideration for the sheath to be fed back. But that's a common practice that you would normally see anyway. So it's not. I don't think it would be surprising for that to be installed.
I suppose, Stephen, as well, for everyone to think about, there is a small bonus feature here that if you think about where these cables come up and are hung off and terminate, you're terminating the 3 phases, and just there, you're also terminating the fiber, making it very easy for us to open that splice box or canister to access the fiber and hook up our CTs to it. There is literally a convenient access point for where we put our sensors, exactly where you need them in this case, right?
Yep. It's maybe also worth adding to that outside of protection in the condition monitoring world, where we're looking at the understanding the health of cables and how that changes over time, and looking for common failure modes of cables, we would also want to be instrumenting the sheath currents in addition to the phase currents. So there could in theory be a system that's doing both protection and condition monitoring at the same time by combining these different measurements together.
Right, a different question here that I think someone was perhaps getting muddled about this terminology of up to 30 sensors and 60 kilometers. So I always garble this and say it wrong, Stephen. So what's the properly worded response to explain that kind of sensor density over range per fiber, so that it's a bit clearer for engineers to kind of wrap their heads around that concept?
Yeah, it just comes to like how this scales up to larger systems. So normally the kind of bottleneck is the optical bandwidth in a single fiber to allow us to represent the full dynamic range of all the CTs that we need, particularly over perhaps high fault current range you know, especially if it's something like 5P30 CTs. Also, the temperature range that they need to operate for in the field, that's another factor. So typically our limit is, you know, something in the region of maybe 24 to 30 sensors sharing that optical bandwidth on one fiber. And as I said, our normal limit for the distance that those sensors can be away from the interrogator and the substation is about 60 kilometers. We've done 62, and that works very effectively. So perhaps it can be extended further, but that's currently our tested limit. So to increase the number of sensors, you can just basically deploy more fibers, or use more of the existing fibers that are likely there in the system, and couple that to another interrogator, and that can scale up what's available.
So I don't know if I'm repeating the message here, but in layperson's terms, the way we try and think about it, but for customers who've heard this for the first time, is for each fiber that we take up to 60 kilometers, you've got a density or a maximum of 30 sensors. If you've got something that requires 60 sensors, you just scale up and take 2 fibers. And to push that envelope even further, if you look at the biggest projects we've delivered, like Dogger Bank, which is one of the world's biggest offshore wind farms, that's thousands of sensors all being networked together by the optical fiber. We're using the fiber for what it was meant for: long range, you know, high fidelity, high speed, high bandwidth, distance communications. It's just that we're using light through the fiber to see all these sensors at the same time. So it's like a concept of range and a concept of density per fiber, and that's how it scales up in these blocks of 20s to 30s per fiber. Right, there is time for one last quick question here. So just picking amongst the bunch, there's maybe a bit more of a commercial deployment question here about what is our view of or use experience of using this sensing technology within the substation fence. So very unfair question to do in 2 minutes, but maybe I'll take a punt at it on behalf of the team just to kind of compress this down. So you've heard Steven and Bogdan say that the ideal way to use our technology is when it's outside the fence, somewhere remote and far away, because it's somewhere inaccessible, somewhere remote, somewhere with poor telecommunications infrastructure or no mobile phone signal, for example. That's where it really comes into its own. And then the data is only generated and shared inside the substation fence by that central unit, the IED, or the interrogator, as we call it, that Steven and Bogdan referred to. We have done programs, digital substation programs, which are to prove the viability and interoperability of 61850 systems, process bus, station bus, this kind of stuff. That has happened. We've even been asked by transmission operators, and we've done it, to deploy our technology to look at multiple feeders in parallel instead of in series, as we showed at the beginning of this webinar. So for example, that could be a centralized digitalized busbar protection scheme, where we're providing the shadow scheme and giving a different failure mode to the conventional electromechanical scheme. And because of the advantages of the lack of infrastructure and equipment, the speed of deployment, and the facility with which it can be installed, you can deploy these things in hours and days rather than days and weeks. And that can be quite powerful. But unfortunately, we don't have time to explain too much more on this one, but we'll follow up with the person who asked this question. And also we've got a track of the other questions here. So for today, because I notice we're out of time, I ought to stop us there. Firstly, thanks to Steven and Bogdan for giving us their precious time and explaining this in such excellent terms and such great detail. We hope that was useful for you. Again, we will provide a video recording on YouTube very soon after this. We'll contact you directly. Our team will follow up with everyone who asks questions. Should you need any further discussion or further in-depth correspondence with us, we'll get in touch with you. And I do apologize, there were a couple of you who asked questions that we didn't get to today, and I'm sorry for that, but we are not ignoring you. We're just respecting people's calendar availability. So thank you very much, everyone, for your time today, and I hope it was useful, and we'll be in touch very soon. Thank you, everyone.
Thank you.